This video lecture will cover about the important procedures in prediction error method, and we give one important result that optimal predictor can be derived in a closed form. We have explicit expression of the optimal predictor when we have the assumed model structure. As we mentioned that the elements of PEM consist of the model structure. This is this is G and H that you assume. You assume that G and H are are used to describe the physical system, the true system. And the second element is you need a form of a predictor, which means that you get to choose filters N and M. And the last one is you will choose a choice of loss function to measure the quantity of the prediction error. Okay, so now if you have those three elements, okay, the procedure goes like this. First of all, you choose a model structure of the form y is a sum function, some transfer function, okay, times u plus again some filter times e, all right, where this is the noise, the true noise corrupted to the system. The noise has covariance lambda, and all the parameter lambda here, all the parameter theta are a set of coefficients in the transfer function in the noise covariance matrix. Then the second step is you will pick a predictor of the form. Your predictor will be a function of y and u. And let me remind that, okay, these filters, N and M, must contain a PO delay. Okay, must contain a PO delay so that your y hat will be a function of y and u up to time t minus 1. Okay, it can be you can only use historical input-output data in order to construct a prediction of y at time t. The next step, the third one, is you select the criterion function v as some function that maps r of theta. This is covariance, right? Covariance of prediction error. So you want this r theta to be small matrix, but then you use a function f to that maps a symmetric matrix to a real number. Okay, so that you can quantify if this covariance matrix is big or small. And then the last step is the model parameter theta hat will be the one that minimize the loss function. Okay. In the following slides, we may use loss function v with a subscript n to note that that v is defined based on using the data of sample size big N. Okay, so try not to get confused between this N as a filter and this N is just a number of sample size. Okay, let me just give some example that PEM is, as you can see, that the prediction error method can be applied to a general model structure, y equals GU plus HE. So the main distinction is that if you pay attention to the noise term, these allow the flexibility that you can model the transfer function H on the part of E. When you see the transfer function times E, it means that the outcome of this box contain the information of ET minus 1, ET minus 2, right? The filter version of a signal contains, it aggregates all the values from the past up to the current time. So this is a main extension from the method we know, such as the linear least square. When you do the linear least square, you assume that if you can apply the linear least square, it means that you can write things like output is some sensor matrix time parameter plus noise, right? Where you see here that for least square, the noise term, this is the noise at time t. You didn't model any dynamics, any historical part of E in the equation. All right, so this is the PEM formulation will provide advantage on this point of view. Okay, now, so it means that least square method is a special case of PEM. So take a look at the ARX model structure. Suppose, of course, you can model it in this way. Your AL is a AR polynomial 1 minus A1L minus A2L square dot AP L to the P. Okay, and then your BL is B1L plus B2L square dot. It depends on you. Suppose it's order R. Okay. Okay. Equivalently, this function is what? Is YT. Everyone know how to write ARX equation? Okay. Can you expand it? City Park.
YT equals
put everything to the right hand side.
BL divided by AL.
Oh no, City Park. You should do it this way. Just apply the polynomial AL.
Okay.
Okay, that's gonna be yes. Okay, now do it.
ก็เป็น B1L บวกไปจนถึง B what the letter is BNL.
Okay, can I do this? Okay. I mean, it's nothing special. Just apply. I mean, this is kind of this is equation you already know. Okay, and then it becomes what? Can you apply the lag operator to YT?
A1 YT minus 1 plus A2 YT minus 2 plus until AP YT minus 3 minus and plus 1 UT minus 1 B1 UT minus 1 plus B2 UT minus 2 until BR UT minus R.
Yes, okay. All right, everyone should be familiar with this ARX. Okay, you just did the homework, and you know that when you put it into least square framework, okay, your theta is going to be A1 dot AP, B1 dot BR. All right, and your regressor matrix, okay, your sensor matrix HT. Oh, I think I just okay.
A function of L equal to 1 plus A1L and on the operator is plus not minus, I think.
What did you say, Toto?
A function of L should be equal to 1 plus A1 times L plus using plus operator, not minus.
Yeah, right. Okay, I should put it this way, and then it becomes minus and minus everything here. Okay, and then in the regressor matrix, you see that it contains all the lag information of the input and lag information of the output. All right. In the least square, we know that what we minimize is the residual error. So, and residual error is of course YT minus H theta, and the definition of the least square is minimize the sum square error of the error. And then once you solve for theta hat, what you do is to predict y at time t, you use theta hat and multiply with the sensor matrix. Okay, and of course, when you take a look at this form, h times theta hat is basically, if you look at this, right? If I point it out, okay, this is actually your y hat. If I put hat here, right? Your theta hat at time t. So everyone see that it is actually 1 minus a hat l plus b, the polynomial b, all right, times ut. Is that clear? Because 1 minus a hat l, right, is what? 1 minus a is actually minus a1 l plus a2 l squared dot dot dot, right? a p l to the p. It's actually this part, 1 minus a hat l times y, and b hat times u is the the pink term. Okay, now let's take a look at the at this polynomial. This is supposed to be, okay, when you look at this term, your y hat, right, is a function of your y, the actual measurements, and the function of input. Now, can you see that, I mean, you can take a look at this as, you know, some filter n times yt plus some filter m times ut, right? And that's why we say that actually least square method can be interpreted as a prediction error method. But now take a look at the filter n. Okay, as we have the requirement that any predictor must be in this general form, and the filter n and m must contain a pure delay. So when you when the input argument in the lag operator is 0, it should return 0 in the filter value. Does it is it satisfied for this example? Okay, n at time 0 is actually what? 1 minus a hat at time, not at time 0, at the input argument 0, right? Okay, what is it total? When L is 0, what is the result?
Equal to 0. 1. 1
Why
minus
1?
0.
Look at this.
Oh, I'm sorry. Equal to 0.
Equal to 0. All right. What about m? M at not at time, at the lag operator equal to 0. Kanatat, your m is b hat l.
Is that also 0?
It is also 0. All right. So the conclusion here is that your as an example, your least square method, the predictions that that is given by the the regression model, which is y hat in this form, is actually in the form of a predictor, and the filter in the predictor satisfy the description or the requirement of a predictor. Okay, so y hat only use the information of y and u up to time t minus 1. Okay, and in this case, what is the loss function? We see that the loss function is a sum square error, sum square of the prediction error. So your your r theta is actually a scalar in this case, right? Because your output is a scalar, and then this is the same as the trace because it's a scalar. So your loss function is actually the choice of the trace of covariance matrix. Okay, but Now I would like to give one important result. You see that as the procedure of PEM, the second step requires a choice of the predictor. Now we're going to give you the theoretical result that there's a form of N and M that is optimal, that can be shown to be optimal. So now we're going to start. Start from the problem setting. Suppose your Y is an output of a general linear model structure, Y equals GU plus HE. The noise has a covariance lambda, and the noise is white. The noise white noise. Okay, lambda is a covariant matrix. Delta here is a delta function in discrete time. We have assumptions that G at time 0 is not at time 0. L, all right, when L is 0, G0 is 0, which means your YT can only be a function of U up to time T minus 1. Okay, and this is a requirement, another requirement in the general model structure. H at 0 must be identity. You just normalize the gain from the noise to Y to be unit. Okay, and we have assumptions also. This is the assumption that we mentioned when we talk about the model class, that these transfer function must be asymptotically stable. What do we mean by, transfer function are stable? Ping?
It means that the stat is going to 0 when T is going to infinity.
I'm talking about transfer function. Transfer function is stable?
Mean that it go into any constant when L is going to infinity. Or T going.
What goes to 0? What goes to infinity? Can you clarify that again? I'm talking about transfer function.
Well, when we talk about then for function, Laplace is going to 0. Yeah.
You mean transfer function as a matrix go to 0? Ping. That's the important concept in control system. Can you review? Talk. I would like to check from, with student outside control lab if you are recalled by this description. Ping. Talk. What do we mean when we say transfer function is stable?
I think all the root is in the unit circle.
Yes. Okay. When we talk about in discrete time, right? A transfer function, a rational transfer function, can be represented as numerator, quotient of numerator and denominator. And we say a transfer function is stable if the roots of denominator polynomial stay inside the unit circle. This is discrete time. Okay. In another word, the impulse response of Hz, which is a sequence of hk, right? When k is an integer, the impulse response go to 0 as k go to infinity. All right. Okay. I hope this is something that you should keep in mind all the time when we talk about the system is stable, the transfer function is stable, and those things. Okay, but let me point out that the requirement or the assumption in the yellow area here are not clearly seen yet when we talk about the model class. We didn't give you the full explanation yet why we require this one. But in this slide, it will be clear to us after we present that the optimal predictor would be this way. Okay. We have the third assumption that the input and the noise are uncorrelated. Okay, whenever t is less than s. Okay, so now the whole point is that I'm going to give you the expression of the predictor and how to derive that. Okay, now let's say that when we talk about the optimal predictor, we're gonna we're gonna take a look at the prediction error. Okay, and basically we're gonna look at the mean square error of this guy, the mean square error of the prediction error, and then we're gonna say that the predictor of the optimal predictor is the one that has the smallest MSE. Okay, it's optimal in the MSE sense. Okay, first we're gonna start from the we're gonna start from the general model structure y equals GU plus HE. But then we can split HE into H minus IE plus E. Okay, we add and subtract. And then the next step is, of course, from this equation, can someone write E in terms of Y and U instead? Napat, are you here? Napat is not here. Okay. Ping, can you write E in terms of Y and U by looking at the equation in the green line, green box?
Being equal to y minus gu. Mm-hmm. 8 multiplied by h inverse.
Okay, all right. Just subtract GU from Y and apply H inverse, right? So it's going to be H inverse Y minus H inverse GU. Okay, so I'm just gonna plug that in on this expression. Okay, plug E in here, and then when we just plug it in with just some algebra, just an arranged thing, we end up with the third equation. Okay, but here I would like to say that this is something you can view as the term inside the yellow bracket with the noise. Okay, the term in the yellow bracket basically a function of it's a function of u and y. Okay, so the term in the bracket we call it a ZT. Now let's take a look at this closely. Okay, first of all, you see that ZT contains what? We look at this as a some filter version of UT, some filter version of YT, right? We talk about ZT now. And then with the assumption that your G must be 0 when L is 0. Okay, so let me ask you on the first term. With this assumption, it means that the first term is a function of UT. I mean, the first term, can the first term be a function of UT? Or it can be a function of U at up to time t minus 1.
Function of time t minus 1 because when t 0 equal to 0.
It's not t equals 0 here. Again, this G, yes, G is a function of the lag operator. All right. What about the second term? Okay, City Park. We have the assumption that h of 0 must be I. Okay. So it means that if you evaluate the term in the bracket, in the circle that this circle, when you evaluate L equals 0, that goes to City Park.
That goes to 0.
Okay, which means the second term can be a function of yt, or it can be a function of y at up to time t minus 1.
y at the time t minus 1.
Not at time t minus 1, up to time t minus 1.
Up to
Yes,
t minus
can be a function of past y, right? Y0, y1, all the way up to time t minus 1. Okay, so I'm gonna clear it up and conclude that actually ZT contains the information of input and output up to time t minus 1. Then can we conclude that ZT and ET are uncorrelated? They are uncorrelated because the assumption that U and the noise are uncorrelated when the T argument, the time argument of U is less than S, which is the argument of E. The past input will be uncorrelated with the current noise. This is part of our assumption, all right? So that's one thing. Another thing is that because your because your ZT can only consist of the past information of the output. Okay, so if you take a look at this, your Y, all right, your YT, now we look at this, your YT, if you look at the YT can be a function of ET minus 1 and ... E0, right? Because as I said, this box is a filter version of noise. So it contains all the information of noise from the past up to time ET. Because the filter H, they might have constant, right? H of 0 is equal to I. But then if you take a look at Y at time t minus 1, of course, it can be a function of E. Totok, are you here?
T minus 1.
T minus 1, T minus,
And
T minus 2, and so on, right? So if I ask, okay, why T minus 1, is it uncorrelated with ET? Totok?
yes.
Yes, right, because YT minus 1 only contain past noise. Sorry, YT minus 1 can only contain the noise at time up to T minus 1. But the noise itself, you assume it to be white noise. So YT minus 1 and ET must be uncorrelated. Okay, so with these two facts, we conclude that ZT and ET are uncorrelated. Okay, what do we mean by being uncorrelated statistically? Kanatat, what is this definition? We say the two processes are uncorrelated if
I don't know.
Okay, if you don't know, how can we review this? What would be what would be a good way to keep up with the lecture? Totok.
It means that expectation of ZT times ET equal to 0.
Expectation of ZT and what?
ET.
Okay.
Transpose equal to 0.
Okay. Let me remind you that is Z at, for process, okay, is ZT and E at time S where T can be, it can be made unequal to S, all right? Because usually when you look at two signals, you look at the correlation function, right? Correlation function is not like a random variable. That correlation is a constant. Okay, so when you say that, oh, this correlation function is 0, it's actually a function that is entirely 0 for all t. Okay. All right. When these two guys are uncorrelated, then now we get to the important point that, okay, now let's examine. Suppose you have a predictor y hat. Now we say in general that this can be arbitrary predictor of yt. Okay, and then you look at the prediction error. You compute what expectation of et transpose that represents the covariance matrix, right? The covariance matrix of et as a function of time as well. Oh, sorry, this is the covariance of et of the error at lag 0, and then you just plug in the expression of y hat here. Oh, sorry, no, that's not y hat, that's yt. Your yt is zt plus et, so you put it here. Now this is quadratic form. Okay, this is quadratic form. Now I would like you to group. Now I'm going to write zt minus z hat t plus et. Okay. Now if you just multiply these two guys, okay. Can you expand this whole thing by and grouping these as one term and one term? Sitipak, can you multiply?
ct minus y hat t multiply with ct minus y hat t transpose.
Yes.
Plus ct minus y hat t multiply with et transpose. Et transpose and plus et multiply with zt minus y hat t transpose. And plus et multiply with et transpose.
Okay. Okay, this is the expression. And what we're gonna do with this expression is to take what? Expectation, right? We're gonna take expectation, and you see that first of all, I would like to pay attention to the term in the pink area. When you take expectation, it means that you're going to find the correlation between the blue and the green term, right? If you take expectation, it's the same as finding the correlation of zt minus y hat and et. Okay, but what we just know about zt previously, zt and et are uncorrelated, right? Okay, now I'm just going to use the notation like perpendicular. Zt and et are uncorrelated. What about y hat t and et? Do we know something about these two guys? Are they uncorrelated? Toto?
Because y hat t is function until time t minus 1, so y hat t and et are uncorrelated.
Yes, very good. Y hat as a description, as a requirement of being a predictor, it can only contain the past input and past output. So it must be uncorrelated with the current noise. Okay, so it means that this guy, the term in the pink area, in the pink box, go to 0 after taking the expectation. All right, everyone got it? So then we have the remaining term is the expectation of the blue terms, okay, which is this, and the expectation of et transpose, that's the covariance matrix lambda. So if I clear up the whole thing, okay, it just says that whenever you use any predictor y hat, right, the covariance matrix can be decomposed as two terms always. This is and all these two terms, these are non-negative, right? Expectation of quadratic form, always non-negative. Plus the noise covariance, which is supposed to be non-negative as well. Then if you get to pick the form of y hat, at this point we have derived covariance matrix after we use any arbitrary predictor y hat. But which y hat that gives you the smallest covariance matrix, right? I mean, how do we do it? I mean, here you cannot do anything about this term because this is constant. But if you look at the first term, it can be made arbitrarily small by choosing y hat to be zt, right? I mean, you can control this green term by picking the choice of the y hat. So why don't we make this term, the green term, go to 0, which means you pick y hat t equals zt. Is it satisfy that? I mean, does this choice satisfy the assumption of being a predictor? zt. Now take a look at the form of zt again. We just mentioned that zt is a function of u and y, and is a function of past input and past outputs. So this choice is valid. In conclusion, that means in conclusion, you pick y hat equal to zt, and that gives you the optimal predictor in the MSE sense. MSE sense means square error. It means that the covariance of the prediction error is smallest. You cannot make it 0 because you see that the residual, the irreducible term still depends on the noise covariance matrix. But that is the smallest quantity you can do for the covariance. All right. So here, conclusion: optimal predictor is given by the form in the yellow area. When you just copy the term here from the blue box, that's the representation of zt. Okay. And then when we put it back into when we use this form in calculating the prediction error, that is going to be the optimal one. Okay. You see that after you put it back, y equals du plus he, okay, you just subtract y hat, from the yellow area, from the expression of yt, you will see that it turns out to be the true noise covariance. This is the important result, all right, which means we assume that your true system is described by this equation. Again, you assume that this is your DGP. Okay, and at this point, if you know the true description of the system, you use the information of H and G in order to construct an optimal predictor. All right, because you need H and G to construct the filter N and to construct the filter M. When that applies, okay, the optimal prediction error will be the true noise. Okay, and then when you just arrange everything, rearrange the expression, the optimal prediction error is given by this polynomial. This expression. If you take a look at this closely, all right, this is just like what we had before. Y equals du plus e, and e is what? Y minus du, the whole thing, multiplied with H inverse. Okay. And if we take a look at here, if I just expand and I see how is a function of y and u, you will see the expression of what? Your noise covariance, your prediction error, your prediction error is some filter applied to yt and some filter applied to ut. Okay, and now it fully explains why you need these two transfer functions to be stable. You need H inverse and H inverse G to be asymptotically stable. Why, Sitipak? What happens if any of these two transfer functions are not stable? Sitipak?
The error will be not bound, will be unbound.
Right, correct. If that assumption doesn't hold, it means that your prediction error can be diverged, which means the whole point of prediction failed, right? This doesn't mean, I mean, you know that if you if the actual YT is increasing, if the prediction works well, the prediction will go increasing as well, right? But you want the error to be small, to be bounded. Okay, so that's explain the requirement. Now we take a look at this one example in order to apply this result, which is nothing. It's just to substitute the transfer function. Let's say, okay, you have an Rmax model. Rmax model means that you have autoregressive term, you have moving average term, and then you have exogenous input. Okay, U and U is a zero mean white noise. Now, can you arrange into Y equals GU plus HE? Okay, so first of all, you will see that these can be written as 1 plus AL YT equals BL, right? UT plus 1 plus CL ET. Okay, write it in terms of some polynomial applied to the signal. And then, of course, we can write it into BL over 1 plus AL U plus 1 plus CL over 1 plus AL. That is the polynomial G, that is transfer function G, that's transfer function H, given by this. Now, what I'm doing is nothing, because I know we have learned that the optimal predictor must be in this form, H inverse G times U, 1 or identity minus H inverse times Y. So I just plug that in the formula. Plug that formula, and it gives us these results, the yellow term. With this, okay, we will show clearly later what do we do with this expression of y hat. Okay, but before that, I would like to mention that the way you compute the y hat is not, I mean, of course, this is represented in terms of the transfer function, but because of this example, Rmax example, you see that the denominator of G and H is common, right? Is given by 1 plus CL. So what I can do is, of course, I can just move things up, and then, okay, I can do it here as well. In order to compute y hat, I can just write it like this. C minus A times LYT. Okay, so I can transform it into the recursive equation in time domain again. So what I have is going to be y hat t, all right, and plus c y hat t minus 1 equals b u t minus 1 plus c minus a y t minus 1. So the equation in the green font is actually the same as the description in terms of transfer function. But this is a recursive equation that you can iteratively compute, right, by initializing some initial values, and then you progress the step. For prediction error, okay, of course we apply the formula from here, okay, with just plug in the expression of h and g, and what we get is the term in the red area. And then with the same thing, the expression of the prediction error as a you know, in terms of the transfer function multiplied with y and u, you can also write it equivalently in terms of the recursive equation. Okay, and in order to compute the prediction error and y hat, as I mentioned, you will just initialize some values, and if you initialize the error at time 0 as 0, it means that it's equivalent to y hat at time 0 equal to y0. Okay, but the choice of initialization is not a big deal. I mean, of course, you can initialize it with what? With 0. With this choice, your prediction error at 0 would be non-zero, right? Would be y at time 0. But the transient is not significant as the time progresses.
If it does it should be BL in the prediction error in the red box.
In the red box, BL.
No.
Yes. Right here. Okay, thank you. BL. All right. So then this step, what we just showed you is that, okay, if you have the general linear model structure, this is the form of the optimal predictor. Now it gives us the remaining step, that but how can we pick the parameter theta hat that minimize the loss function? All right. So we just plug this in. Now you get the form of the prediction error. You plug it in, you compute the covariance matrix, and then you minimize the loss function. That is given by this slide. Okay. Probably maybe I break to another video, or should I? Maybe I should go for the rest. Okay. Let's just make it complete. For the remaining step, this is the loss function minimization. Okay, when you get the form of the prediction error, you form the covariance matrix, and you pick a choice of the loss function f. Remember that this f, it just determines how big the covariance matrix is as a scalar value. And of course, what you will do with this cost objective is you're gonna minimize it over theta, and this is unconstrained problem from optimization point of view. So we refer to some iterative method like Newton-Raphson, or the gradient descent. So these are the method that says, okay, please please using iterative formula, the next theta would be the current value of theta plus some step size, right? Multiply with some search direction. And the choice of the search direction just signify the numerical method. The search direction for the Newton-Raphson is going to be what? It's going to be the Hessian of V, right? Inverse times the gradient of V. For the gradient descent, the search direction would be the negative gradient, things like that. So these are some some information from optimization point of view. But let me just explain that in order to implement those numerical methods to find a local minimum of V, basically at least we need gradient information about V. And here I just would like to sketch the idea that in order to get the gradient of V, you need to apply the chain rule, because V is defined as your loss function f of the covariant matrix. So when you take the gradient of V respect to theta, so you need to take the gradient of f respect to r. Okay, the choice of f as a function of r, as we see two examples, right? Trace, this is a function trace, and this is a function of determinant. Of course, del f by del x would be different. Depends on the description here. If f is linear, del f by del x is going to be w. For this, it will involve something. We will check from the metric calculus. So conceptually, our gradient of V depends on, so first is del f by del r, and the rest is, of course, you need to take the derivative of this guy with respect to theta. Okay. And that's going to be, this is a matrix, okay? You need to take the derivative of this matrix with respect to theta. But now it's just going to be maybe a little bit complicated if you just take a look at this general form. So let me reduce to a simpler case, which means scalar system when the error is a scalar, okay? And when you use just the trace function. So in that case, your cost of objective reduces to the sum square of the prediction error. So the gradient would be, I hope everyone can do it. When you take the gradient of V respect to theta, of course, this is quadratic, okay? Then you take quadratic and then you apply the chain rule. Okay, and now let me emphasize on this. When you take the chain rule, the derivative of the error with respect to theta, theta is usually a vector, right? Like for in this example, your theta is A, B, and C. So that's why this term is usually a gradient vector. Okay. The gradient of the vector, the gradient of the prediction error, okay, I put a note here, is typically nonlinear in the parameter theta. Let's take a look. When we have, okay, now if I just again take a look at the special case of Rmax now, this is ARMA 1.1. Okay. Here we derive the optimal predictor of Rmax, right? Rmax 1.1.1. So if I consider a special case of Rmax, which is ARMA, then which term goes away? Sitipak?
The U term.
Okay, the U term disappear. So then the optimal prediction error is given by this. Okay. And then, okay, let's just examine, okay, if in the procedure of minimizing the loss function, you need the gradient of E respect to A and L. You see that, okay, if you take the gradient respect to the parameter, then you get what? A, right? Sorry, L, just L. When you take the gradient respect to C, of course, it's in the denominator, you get this square, and then you have the minus sign. Should I? This should be another L. Yes, sorry. This should be another L in here when you take the gradient, right? Everyone follow this? When you take the gradient of this guy respect to C, so you get 1 plus CL square, right? But then you need to apply the chain rule, right? Chain rule. So you look at this term, take the derivative respect to C, and then you get L. Okay, so the L is missing. And then when you arrange, this is YT, okay? But because you know that this is the same as I split the quadratic term as the product, okay? And I know that the term here is actually what? The term here, the term in the green box is actually what? The prediction error. Okay, so now I can just write the gradient of the error in terms of the error. So it's L over 1 plus CL. I need to correct the slide on page 60. Okay. Now this is an illustration that, okay, this is how you compute the gradient. And of course, again, let me emphasize that you see the gradient with respect to the parameter, it is nonlinear function in the parameter. Because this is a transfer function, right? And I mean, if you just work it out, how is a function of CL, then you need to, you know how it works, right? For example, this is going to be L 1 plus 1 plus CL is going to be what? It's going to be 1 plus CL and plus CL square dot dot dot, right? YT. Oh, with the minus, plus and minus. Okay, and then you see that you have C square, C cube, and so on. So the gradient of the optimal error is typically nonlinear in the parameter. That's why the whole point of these loss function minimization, we say in general that it ends up with nonlinear optimization. With that in mind, you know that when you apply numerical method for nonlinear optimization, of course, you will need what? Initialization, right? When I just mentioned that, okay, when you apply iterative method, whether it's going to be gradient or the Newton, you say the new theta is the current theta plus step size or and the search direction. And of course, that's going to be the first step, the very first step that you need to initialize with some number, with some value, and then to update the step and so on. That's why typically here, if you apply system identification toolbox PEM command, the input arguments of PEM, of course, it will require, this is mandatory input argument, which is the data input output data set. And also it requires the initial parameter at iteration 0 for the search method in optimization. And currently the PEM command in system identification toolbox also handle the problem that not only with the unconstrained version, but if you have some assumption on theta that, okay, theta is bounded by, lower bound and upper bound. Okay, this is part of the constraint. The toolbox also provide a constrained optimization process for you. So you can impose a constraint of theta if there's any. This is optional. Okay. All right. Let me end this video clip by providing some numerical example. I have a true system DGP as Rmax 222 given by this. This is AR part, exogenous input part, and the moving average part. Okay. And U and V are both white noise with the unit variance. But I generate U as a binary signal and independent of V, independent of E. Okay. My input is in the blue curve and the output in the red curve. So you see here that, of course, the output will be filter version of the input plus some noise. And here we use ARMA I mean, with the moving average term, the noise, not only the noise at the time t will have an effect on yt, but also it kind of aggregates the information of noise in the past for yt as well. Now I consider three models classes. Sorry, three models, just three models. The first one is RMAX 222. Now I intend to pick the same model structure as the true system. So the first choice is this. The second choice is I choose the model class to be the same as the true system, but I neglect, actually I should say that I pick ARMA. Okay, sorry. I mean RMAX 22, which means, is ARMA 22, which means I neglect the information of the input in the estimation. Everyone recall what the ARMA process is? Is polynomial moving, autoregressive polynomial applied to yt equals to some polynomial applied to the noise. Okay, so here there is no term in exogenous input. So with the second choice of the model, I choose the model class incorrectly. Okay. For the third choice, I pick error x. What is error x? AYT plus BUT plus noise, error x. Then with this choice, it means that I didn't assume any noise dynamic. I thought that only the present noise will have an effect on the current output. Okay, with this assumption, with this experiment setting, Kanatak, which model structure, which model class should perform best without even doing the simulation? Kanatak.
Is that ARX?
ARX, why? The third model?
Yes.
Because
it's no consideration about noise.
Because it has no consideration about the noise. What about other things? Totok, what do you think?
The first model will be the best, I think.
Because
it is the most complex model. When we use the most complex model, it can model the system in the better way.
Okay, Totok thinks the first model is the most complex one, so it should be the best one. Kanata think that ARX should be the best because ARX doesn't include the noise dynamic. City Park, what do you think?
I think RMAX is the best estimate.
Because
it use an information of noise and input from the past until the t-1 to predict the output at time t. So it's accurate than other model.
Yes, it should provide a more accurate result than other model. What about ping? What do you think?
I also think RMAT is because it includes everything, noise. Yeah, it's good then.
Okay, so if we just take a look at the model class, but without the order, just neglect about the model order for now. These choices of model have different structures, right? The most general structure would be RMAX because it includes autoregressive, moving average, and exogenous. But having all the elements, the most complex one, doesn't always mean that it's going to provide the best best results. Let me remind that our true system DGP is Rmax. I mean, actually, in real life, in application, you don't have this information. You don't know what the true system class would be, but this is this example just to illustrate the result. So what we intend, we are the one who create the true system, and we kind of see that, okay, if we use different models in the estimation, which one would provide the best result? It's kind of we have the true system for us to look up. We know that the actual system is this, and then I will conclude that, okay, the first choice would be the best one because it corresponds to the same model class as the true system. But what Totok said is not generally true. What you said is that, oh, the most complex one would be the best one, because if I include Rmax model and I pick like 10, 10, 10, what do you think, Totok? The Rmax 10, 10, 10 would be more complex than Rmax 2, 2, 2, right? At this point, we don't know yet which one should be better, because both of them correspond to the same model class as the true system. All right, but the complexity here are different. This is going to be important issue when we talk about the model selection. I will emphasize this discussion again. So this point, to compare these three models, we can say, we can conclude without doing the simulation that okay, sorry, this is ARMA. Okay, ARMA, of course, is gonna provide worse result, not worse, but it cannot be as good as Rmax because you don't use input. How come you don't use input? I mean, the actual YT depends on the input, right? So using input as a part of information in the system ident should help you to estimate the system better. For ARX, why it cannot be as good as Rmax? Because the actual Y, right, depends not only on ET minus 1 and all the parts of ET, okay? While using ARX only consider the effect on ET. So including the noise dynamics as you know, introducing the transfer function H should provide a better result. And as we can see from this, if you see the fitting percent, the larger the better. Rmax 222 provide a better prediction accuracy. Okay, and we compare with maybe the graph is not quite clear. We compare with the gray line. The gray line is the measurement. Okay. Okay, this is some example of the codes. When you generate some identification input, right? You can use ID input. This is a command in System Ident Toolbox. You can have an option PRBS, white noise, binary, and so on. For E, I generate white noise using Gaussian white noise, RAN-N. Okay, and then for the DGP, I use ID poly command. This is polynomial A, autoregressive polynomial. This is the exogenous input, B polynomial. This is a moving average polynomial. And then if you put the noise variance, so the DGP recognizes that, oh, the noise term will be equipped with this variance. You put TS equals 1, so it's going to recognize that, oh, this is the discrete time. All right. When you do the simulation, when I produce the actual YT, I use the sim command with this system DGP, but I also put an option that says, when you simulate the response, please add the noise. Okay, please add the noise. And the noise that I add is in the profile vector of ET. Okay, and when we perform the identification, the thing is you can use PEM as well. You can use PEM, but because the model structure here is Rmax, Arma, and ARX, so you can directly use Rmax command, which is, I mean, it provides dedicated algorithm for model structure of Rmax directly. Okay, so you provide data. Okay, the code is not here, is not completed because you need to assign data as that. All right, so you can use ID data command and you put Y and U. Okay, and then it returns the model M and M1, M2. That's going to be a model variable in MATLAB, and you can use the command compare. This is to compare 3 models and with the system identification data that. And here there's some options of the command compare. Here's I think there's a simulation mode and prediction mode. So I put 1 to compare one-step prediction. Okay. For the rest, we can continue after the midterm. I would like to end the video clip. Okay, maybe I just finish it. After we see the concept of the PEM, we see that there's some computational aspects that we can split into 2 cases. The first one is that for the PEM method, some analytical solution exists. For example, if your predictor is a linear function of the parameter, you can write y hat as some sensor matrix times theta. And when your criterion function is simple enough, for example, if the trace of the covariance matrix, you will see that in this case, your prediction error would be your prediction error would be yt minus y hat, right? And that gives you yt minus ht theta. And when the choice of the loss function is the trace of covariance, that turns out to be the sum square of the prediction error. Okay, the sum square. I hope that you can expand everything and verify this. Okay, and when y hat is linear in theta, it means that your prediction error is also a linear function of theta. And now it turns out that the loss function turns out to be just the true norm of the prediction error. And that is equivalent to the least square method. And as we see the lecture of the least square method before, I mean, the solution is in closed form. You can derive explicitly. So in this, with this note, it holds for ARX model or FIR model, but not for ARX, not for Rmax or the output error models. Of course, another case is that no analytical exists, just like the example that we see previously for ARMA Rmax model. There is no closed form because generally the loss function is a nonlinear function in theta, and it involves some nonlinear optimization to find the parameter. And those numerical algorithms include things like Newton-Raphson gradient-based methods. And when you encounter this situation, please make a note that the problem, the unconstrained minimization problem, could have this issue that it may contain many local minima. So what you can do is you initialize theta 0 by several choice. And the way you provide this should be kind of realistic. Sometimes you can get some prior knowledge about theta. Maybe you solve theta from using simpler model structure first, and then use the results as an initial parameter of the model in consideration. Okay, when you apply numerical method for nonlinear model, there's going to be issues with the computational cost and convergence rate and the choice of initialization that I just said. Okay, different choice could end up with different local minima. So you just compare that which one give you the lower one. Okay. I would like to end the lecture today at this point. But we have something for the rest, but we can discuss after the midterm.